More than 2,000 years ago, long before satellites mapped the Earth and computers simulated the universe, one man quietly changed the way human beings think. He did not conquer lands. He did not lead armies. He did not invent machines. Instead, he organized thought itself. His name was Euclid. Today, we know surprisingly little about him. We do not know his exact birthplace. We do not know the year he was born or the year he died. No portraits of him survive. And yet, his influence is so deep that nearly every student who has ever drawn a triangle has worked within the framework he created. Euclid lived around 300 BCE, in the ancient city of Alexandria. At the time, Alexandria was not just a city, it was the intellectual heart of the world. Founded by Alexander the Great, it brought together ideas from Greece, Egypt, Babylon, and beyond. Scholars traveled from distant lands to study astronomy, medicine, philosophy, engineering, and mathematics. Its library aimed to collect all human knowledge. It was in this city of ideas that Euclid taught and wrote a book that would shape education for over 2,000 years. The book was called Elements. At first glance, Elements does not seem extraordinary. There are no heroic stories or dramatic language. It begins quietly, almost humbly, with definitions. A point is that which has no part. A line is breadthless length. A straight line lies evenly with the points on itself. Simple statements. Almost dull, but hidden inside this simplicity was a revolution. Before Euclid, mathematics existed mainly as practical knowledge. Ancient civilizations knew how to measure land, build structures, and observe the heavens. Their mathematics worked, but it was largely empirical. Rules were followed because they gave correct results, not because anyone had proven why they worked. Euclid changed that forever. He asked a question no one had fully asked before: what can be proven, and how do we know it is true? Instead of collecting formulas, Euclid built a logical system. He began with a small set of definitions, common notions, and postulates, assumptions so basic they seemed obvious. From these foundations, he constructed an entire world of geometry using pure reasoning. Every proposition in Elements follows logically from what comes before it. No shortcuts. No appeals to intuition. Every step justified. This was geometry not as drawing, but as logic. Euclid showed that mathematics is not about shapes alone, it is about reasoning carefully from first principles. His method became the blueprint not only for mathematics, but for rational thinking itself. One part of Elements would later become famous and controversial. Euclid's fifth postulate, often called the parallel postulate, did not feel as self-evident as the others. For centuries, mathematicians tried to prove it using Euclid's earlier assumptions. They failed. Again and again. What they did not realize was that this struggle would eventually lead to the discovery of non-Euclidean geometry, new kinds of spaces where Euclid's rules no longer apply. Much later, these ideas would play a role in Einstein's theory of relativity and our modern understanding of the universe. Euclid himself did not know this. But his honesty mattered. He understood that if something could not be proven, it must be clearly stated as an assumption. That intellectual integrity became one of his greatest legacies. Elements consists of 13 books. Together, they cover plane geometry, number theory, irrational magnitudes, and solid geometry. Euclid proved results students still learn today, including the Pythagorean theorem and the infinitude of prime numbers. These ideas were not merely discovered, they were organized into a coherent logical structure. For over 2,000 years, Elements was the most successful textbook in history. It was copied by hand in ancient Greece, translated into Arabic during the Islamic Golden Age, preserved and expanded by Muslim scholars, and later reintroduced to Europe through Latin translations. Medieval universities taught it. Renaissance thinkers studied it. Early scientists admired its clarity. To learn mathematics was to learn Euclid. His influence reached far beyond geometry. Philosophers admired the structure of Elements. Thinkers like Spinoza attempted to write philosophy in Euclidean style, beginning with definitions and axioms and proceeding through logical proofs. Scientists adopted the idea that knowledge should be organized, justified, and logically connected. Even today, modern textbooks follow Euclid's template, and yet, Euclid himself remains distant. Unlike Plato or Aristotle, we have no surviving personal writings beyond his mathematical work. Legends tell us that when a student asked what benefit geometry provided, Euclid ordered a coin to be given to him, saying that he must profit from learning. Whether the story is true or not, it captures something essential about Euclid's philosophy. Knowledge, to him, had value beyond usefulness. Geometry was not important because it built bridges or surveyed land. It was important because it trained the mind. Following a Euclidean proof requires patience. You cannot skip steps. You cannot rely on guesswork. You must follow the logic wherever it leads. This discipline shaped education itself. For centuries, geometry was taught not because everyone would become a mathematician, but because it taught people how to think clearly. At this point, Let us pause the story for a moment. Where are you reading or listening from? Are you a student, a teacher, an engineer, or simply someone curious about mathematics? Euclid's ideas crossed borders, cultures, and centuries. They belong to all of us. Eventually, mathematicians discovered that Euclidean geometry was not the only possible geometry. Space could curve. Parallel lines could behave differently. Euclid's rules did not always describe physical reality at cosmic scales. But this did not diminish his importance. On the contrary, it revealed his deeper genius. Euclid never claimed his geometry described the universe absolutely. He showed how knowledge is built from assumptions. Change the assumptions, and the system changes. That insight lies at the heart of modern mathematics and science. Today, students still learn Euclidean geometry. They still prove theorems. They still struggle with logical steps. And in doing so, they participate in a tradition older than most nations. Euclid did not invent geometry. He gave it structure. He did not discover logic. He demonstrated its power. He did not seek fame, but he achieved immortality through clarity. In a world that often values speed over depth and opinion over proof, Euclid's work remains quietly radical. He reminds us that truth is built step by step, that understanding requires patience, and that the most powerful revolutions are sometimes the quietest ones. If you enjoy stories like this, where mathematics is told through history, logic, and human thought, then you are in the right place. Subscribe to MathsWhisperer. Here, we learn math with stories, not loudly, not hurriedly, but thoughtfully. And in the next episode, we will see how one small question about parallel lines led to entirely new universes of geometry. Stay curious.